So let's now find out how do black holes generate these amazing luminosities. After all, black holes are black because nothing can escape them, not even radiation. The answer is the material around them can still be shining and be observed from far away. Now, we do know that black holes or something like them does exist in galactic nuclei. We know that because of the kinematical tracers, either stars or gas. We know that there is some depth of a potential well, but then right in the middle, there is an extra mass that requires gas or stars to move faster. And so if it's not a black hole, then it's something really similar to it. A lot of mass packed into a very small radius. So for all practical purposes, it is just like black hole, regardless of the details of its physics. Very compact, very large masses near the centers of galaxies. We've seen evidence for it for a variety of reasons, like the motions of water masers in the Seyfert galaxy. Now, about 20 of these that have been studied by now. And they're like point masses. They're like solar system except around giant black hole. And the kinematics indeed indicates that this black hole is some tens of millions of solar masses. In the Milky Way itself, the motions of star near the galactic center indicates that there is an extra point mass there of the order of 3 or 4 million solar masses. And even though it doesn't do much in terms of activity, we know it's there because of its gravitational influence. So something like black holes, or indeed black holes, exist in centers of galaxies, but how do we get energy from them? The key to this is dissipation of binding energy. The fuel gas comes from kiloparsec type radii, say, because of galaxy mergers. The size of the black hole is given by so-called Schwarzschild radius. The formula is given here. For solar mass, that's about 3 kilometers. For a typical large black hole that might power a quasar, which has 100 million solar masses, it will be 300 million kilometers, or about twice the distance of Earth from the Sun. So these really are regions about the size of a solar system. That happens to be also about 10 microparsecs, and therefore the material crosses approximately 8 or 9 orders of magnitude in radius to get to the central engine. Well, that means it will be coming in on roughly radial orbits, but however it does get there, the net amount of energy lost will be a substantial fraction of its rest mass energy. If it could get directly to the Schwarzschild radius, then it could radiate away all of its mc squared. But it doesn't. There is a smallest orbit which is stable. Remember that you can dissipate energy, but not the angular momentum. So the material that falls in has to settle into a small accretion disk. The inner edge of that is the smallest stable orbit. Now, this is very much a general relativity concept. There is no such thing in Newtonian gravity. In Newtonian gravity, you have 2 point masses, you can get as close as you want. In general relativity, no, there is a smallest stable orbit. And so that is how deep the material has to get. And therefore, it will dissipate less than its full mc squared, but fraction thereof. Typically, we think on average it's about 10%. So it doesn't matter what you make black hole from, the regular matter, dark matter, it's just the mass that you know. But there is also a couple other things. In principle, you can also have electric or charge or magnetic field going through a black hole because electromagnetic radiation, so electromagnetic interaction and gravity are the only two infinite range interactions. And black hole can be spinning. So 3 numbers really characterize the black hole. Its mass, its angular momentum, and its electric charge. Now, charges are well mixed in the universe, protons and electrons, so black holes are not likely to have a significant net electric charge. And there, that leaves mass and the angular momentum. For a Schwarzschild black hole, classical black hole, so to speak, the angular momentum is 0. And its radius is given by Schwarzschild formula. The smallest stable orbit around stationary black hole is 3 times the Schwarzschild radius. And this is how close material has to come in order to be eventually absorbed. But how do we know it really is black holes? Well, it turns out there is another way to probe this, and this is from the X-ray emission. The material that's so close to black hole is very hot. It's plasma in millions of degrees of Kelvin, and therefore X-rays are a good way to probe it. There are emission lines in X-rays, which we can use to probe kinematics of the gas, just as we did with non-relativistic cases earlier. And if you have a Newtonian case, there is just a big mass and the stuff is going around, even at relativistic speeds, if you will, then there'll be a two-horn profile, one for gas coming towards you, the other one going away from you. But once we throw in relativity, new things happen. First, there is so-called the transverse Doppler effect. Moving clocks run slower. And then also the beaming boosts the radiation that's coming, or the materials coming towards you, and diminishes the one going away from you. Those two would create asymmetric profile. One horn would be larger than the other. Then there is also gravitational redshift. That's a general relativistic effect. The photons would lose energy getting out of potential well. So the whole thing would be moved towards lower energies. And therefore, you expect broad, asymmetric, shifted line to come out. And that's exactly what's observed. Here is a profile of the X-ray emission line of iron seen in one of the active nuclei. You can see it's very asymmetric and also happens to be redshifted compared to its systemic velocity. And so this is exactly the prediction of what things should happen in case of point mass or something close enough to black hole and the material orbiting around it. So that's probably the most direct evidence that, yes, really close in, what we see are black holes or compact masses compressed to such small sizes that for all practical purposes they're black holes. All right, now what if black hole is spinning? We introduced the spin parameter given by this formula, little a, which is ratio of angular momentum to mass squared and a couple of constants thrown in. This was studied by a physicist named Kerr, and those are called Kerr black holes as opposed to Schwarzschild black holes, which are stationary. And maximum amount of angular momentum that you can put in a black hole, spinning black hole, corresponds to the value of a parameter of 1. For no rotation, it is 0. Now, it turns out that the smallest radius of a smallest stable orbit around a rotating black hole is closer in than it would be for a stationary Schwarzschild black hole. Therefore, you can extract more energy from the spinning black hole, and that's just from stuff falling in. Now, if you can somehow extract rotational kinetic energy from the black hole, then you can get some more. There is a mechanism to do this, and that is if there is a magnetic field threaded through black hole, and it's a mechanism called Blandford-Znaik effect that does this. All right, so this is how you can extract energy, but how much? And we have to now turn to a concept of Eddington limit, which was really introduced in stellar astrophysics, and that's what limits the largest mass stars or most luminous stars. And it works as follows. There is ionized gas, plasma, near the surface of a star, in this case in the region around the black hole. And electrons can be susceptible to radiation pressure, absorb photons, and so there is essentially radiation-driven wind. On the other hand, the gravitational field pulls them back. So for a given mass, there is certain critical luminosity above which the stuff will be blown away by the radiation pressure. And you can compute that using cross-section for absorption, so-called Thomson cross-section for free electrons. And you can put in now so they have outward force due to the photon wind that's pushing on material that's directly proportional to luminosity. And that has to be balanced exactly with the gravitational force, pulling back on now protons and electrons together. Because that's where all the mass is. They just latch to electrons as they're well mixed. So the equation of these gives you the limiting luminosity. If luminosity is larger than that, the radiation pressure wins and the thing blows itself apart. If it's less than that, it can still be in some sort of equilibrium. So the largest luminosity you can have around any given mass is given by this formula, the Eddington luminosity. And that turns out to be of the order of 10 to the 38 ergs times the mass of the object in solar mass units. So for something like 10 to the 8 solar mass black hole, Eddington luminosity will be of the order of 10 to the 46 ergs. Remember that solar luminosity is few times 10 to the 33 ergs. So that will be of the order of 10 to the 13 solar luminosities. And that's about as much as the most luminous quasars that we do see. Next, we will consider collimated emission from black holes in form of radio jets and other phenomena associated with them.